Hi, everyone. Welcome to section 6 of the Symposium on Virtual and Augmented Reality. My name is Francisco Simões. I'm going to be your host today of this session. It's my pleasure to be here to discuss about displays. So we are going to have three great works to be discussing here. We are going to have the video of them. After each of the paper, we are going to have a discussion. Please post your questions on the chat here on YouTube or on Discord. And we are going to start discussing our first work, the BINOV FAR, an efficient binocular visual field assessment method using augmented reality glasses. It's a full paper, a research paper from Dr. Baharul Islam and Arezo Sadehagan from Baheshir University. So please enjoy our first video.
I am Arezu Sadegzadeh presenting our paper entitled BINO-VFAR, an efficient binocular visual field assessment method using augmented reality glasses. Overall, our presentation is composed of 5 main sections: introduction, the challenges of the existing methods, our proposed method, the experimental results, and finally the conclusion and the future research directions. Visual field is the area that human eyes can see while they are focusing on a central fixation point, which is determined by visual field testing. Visual field testing is a regular eye care to discover the vision loss of the people who are at risk. People who are suffering from glaucoma, stroke, diabetes, and high blood pressure. Why do they need these tests? Because the effects of these diseases are required to be continuously monitored, as they can limit the patient's daily activities such as driving. The earliest visual field map testing systems suffer from some limitations. They test each eye separately, so they are time consuming. They are inconvenient and stressful for elderly people and children and need to be performed by an ophthalmologist. Additionally, they can measure only a limited range of visual field. Recently, virtual reality glasses are the most common tools in this field. However, they are also not able to test wide field of view and need to be isolated from the real world, which challenges the patient's concentration. To address the mentioned challenges of the previous systems, we proposed a binocular visual field assessment system named BINO-VFAR, using novel AR glasses for a wide visual field map of 60 by 100 degrees with a short test time of 3 to 4 minutes. In this system, the users calibrate the AR glasses on their eyes based on a central red fixation point and 8 light green static points on the border. The false negative results are minimized by randomly displaying the missing stimulus again. The stimuli presentation rate is adjusted to the subject's response time during the demonstration. In this method, wearing the prescribed glasses by users is also allowed. The materials and experimental setup of our system are illustrated in these two figures. As it is shown, there is a pair of AR glasses which is connected to our PC via a USB cable and an HDMI cable simultaneously. The employed glasses are portable Dreamworld AR glasses. There is also an optical mouse to record the information of the stimuli. The overall flowchart of the proposed system is illustrated in this slide. In the first step, the user is asked to wear their AR glasses and adjust them based on the 8 light green static points shown on the AR glasses and the PC screen. Typing the user's name and starting the test, 60 stimuli are randomly displayed one by one in an arrangement of 6 rows and 10 columns on a white background on the display of the AR glasses. Each stimulus is displayed for 2 seconds, whose intensity is continuously changed from light gray to black. Focusing on the central fixation point, the user is asked to click the mouse when the stimulus is visible for them. The intensities and positions of the displayed stimuli are recorded based on the user's responses. Clicking on the Show Result button, the recorded data of the stimuli are presented. The whole test is completed in the Unity 3D engine. Then the result is resized into a 600 by 1000 visual field map in MATLAB based on the bicubic interpolation. As you can see, the final visual field map is shown after applying the interpolation. This is timing of VF testing process for two consecutive stimuli. Each stimulus appears for 2 seconds. There is a fixed pre-stimulus delay period of half a second between two stimuli. Due to COVID-19 restrictions, we couldn't get access to the real patients in hospitals, so our system was tested on 5 healthy people by artificially blocking some areas of their visual field on their AR glasses. So 16 different combinations were proposed, as you can see here. Here A's are the blocking areas and the AR glasses display, B's are the recorded click data, and C's are the final visual field maps after interpolation. The accuracy rate of our proposed visual field test is presented in this table for 5 different subjects in 15 combinations based on this equation. Average accuracy of 99.93% shows the high performance of our system. The confusion matrix of our visual field test for 5 subjects in all 16 combinations is presented in this table. The high values of true positive and true negative rates and low values of false positive and false negative rates prove the capabilities of our system. Assessing the reproducibility of our system for 3 subjects from 4 combinations, we achieved 99.72% intra-class correlation coefficient between the first and second trial of the subjects from the same test, which is statistically considered as an excellent reproducibility value for the proposed system. Additionally, the repeatability of our test was assessed when there are some strange mistakes in the test and even the users themselves are aware of them, the test can be repeated for them. As you can see here, the existing mistakes of the first try didn't happen anymore in the second try. To conclude, we proposed a binocular visual field testing system based on AR glasses with high accuracy and repeatability and reproducibility capabilities, performing in a wide field of view and short time. However, it relies on subjects to focus on the fixation point. It is performed through 2 platforms of Unity 3D and MATLAB. To overcome these issues, as our future research directions, we will apply gaze detection and tracking system, perform whole system on one single platform and test it on real patients. Thank you very much for your attention. We look forward to your questions if there are any.
So thanks for the nice presentation. It was a great topic to discuss here. Let me see if we have questions from the audience, but I have multiple questions here. It was quite great to read the papers from this session. So I will start with one to break the ice so the others can have time to post the questions on the chat. Please do that at YouTube or Discord. So, Arezzo and Dr. Baharu, it's great to have you here. It's really nice to see your work because also I had some experience with this equipment. So I had some time to make this on an ophthalmologist with a practitioner. And these tests are not so comfortable. So it's great to see this opportunity to have them migrating or trying to migrate to these VR headsets, for example, or AR headsets. So you achieved 99% of accuracy, but you didn't have the opportunity to test with the real patients. I understand that because of the COVID outbreak, so that's not a problem. But how do you compare yourself with these systems that we have? I saw you made a nice comparison, but can you have comments about this approach or the accuracy that you have, how it compares? Because you don't rely on a practitioner, a medical doctor to use the system. Can you make a comment on that?
Okay. Hi everyone. It's nice to see you here. Thank you very much for your time. Yes, of course. But unfortunately, as you said, based on the COVID-19 restrictions, we were limited to having just healthy people in our lab, not going to the hospital. And of course, we can compare it with traditional systems as they are in the hospital. And because we couldn't visit the hospital, so we couldn't compare them or get help from the ophthalmologist. But in our future work, of course, we will just be into details and take some experiments based on the real diseases, for example, glaucoma, or the people who are just suffering from diabetics, what kind of just visual field they have. We will just block that part, or even we will use that patients, and we will just compare the real results from the traditional methods who are available in the hospitals.
Great, thanks for your answer. I also have another doubt because while reading your paper, you mentioned here in your presentation also, you rely on the focusing capability of people on the red dot. So you mentioned it may be a problem if people cannot fix on this red dot. And I can imagine to use some gaze tracking or other options to understand how it works. So I don't know if you have thoughts on that because I saw your analysis on these blocked areas and these things. I was thinking about it's really clever. But how do you intend to access this fixing problem on the red dot? Just with gaze tracking, the gaze trackers are precise enough to do that, but the blinking can make a difference. I don't know if you have comments on that. How do you think to access?
Yes, as in our paper, we also mentioned in our just conclusion part as our future work, uh, just looking at that fixation point is really important because if we want to our use move our gaze, we can see every part of our visual field. I mean, the healthy person's visual field. If we want to move our gaze, and we use this point when we want to just fix the air glasses on our eyes at the first step, we ask the patient to move the gaze and look at all the 8 dots to just see all of them, because if the person can move the gaze, can see every part of the visual field. So we fix the AR glasses based on this just philosophy. But in the later, yes, for applying such kind of things, we will just apply in the future a gaze tracker or such kind of thing. Blinking doesn't make any just difference in the visual field at the end results. I mean, as we just gave some seconds between two stimuli, so blinking doesn't make any changes. And at first, we just asked our patients to be comfortable. And one of the main things that make this person, this of course system, more benefit than the other, I mean the previous traditional one, is that it is comfortable for patients. They can blink, and it's not isolated from the outside, I mean the real world.
That's great. That's great. And just one final doubt that I have, because I made this test with the ophthalmologist, and I remember they asked me, okay, look at the right, look at the left, look up, look down. And then after that, I was trying to reach these points to see if I can find them and click. It's just like the system. I can imagine it's the same test. I'm not sure, of course. But do you have ideas about improvements on your work to maybe guide patients on these movements or something like that? So you are in a augmented reality with an augmented reality device, for example. So do you have ideas about how to guide this process in different tests? I don't know if you thought about these things. Just thinking about next steps in future work.
You mean at the first step, wearing the just glasses, so looking up and down for that 8 fixation point, you mean?
No, to provide guidance to the patient, for example, in a test that you need to say to them to do some movement or to make some movement,
Oh,
to maybe
yeah.
show some clues, some hints on the device, on the
Of course,
display.
before our test, we have demonstration. We just guide all the patients. Even we did our just experiments on the healthy people. We guide them. Our first try was demonstration for them to understand everything, to just get that relaxation and be out of just the tension of the test. Then we start the real test. I mean, the first time we have demonstration and show everything and guide them, then we do the real test.
Great. Thanks for the answers and for the nice discussion. I think we can
Thank
move
you.
now for
And
the next one.
of course, my professor, I just started before him. Sorry, just if he wants to add something, I'm really glad.
Yeah, thank you, Arizu. So, Francisco, it's a very good question regarding your, the gaze fixation point. Okay, it's very, very important, said Arizu, because uh, if patient or user not fix their gaze to the particular point, that means no problem. I mean, their eyes is the healthy eyes. I mean, no patient. So gaze fixation point is very, very important. So our future work actually, we are waiting for some device is not available in here. We already order it from outside of Turkey, but it needs some time to arrive here. So that one is look like our future plan. Okay, suppose patient not fix their point to the center point, red dot you saw. Okay, so probably all the test will be paused. Our plan is look like this. Okay, so you cannot perform the test if you cannot focus your point to the, I mean, the fixation point. Okay, your guess, because it will continuously measure your where you focusing. Okay, so that means actually it will be more authentic. Okay, so it's actually in our future work plan. Okay, but
That's great.
somehow it's COVID restriction actually limited us. Okay, for example, delay of the equipment, or we cannot go for real patient in hospital, or we cannot cross match our result with the the other Humphrey based traditional method result. Okay, so our plan is look like this. We will collaborate with an ophthalmologist, then we bring our system to the eye institute or eye clean eye hospital. Okay, so then patient will test the traditional method and also test our method, then we compare our result with that method. Okay, then we will take some feedback from the patient plus ophthalmologist, then actually it will be more useful for our method, right? So
Yeah, I
but
see.
somehow it's our future
That's
work
great.
plan because of COVID-19.
Yeah, I understand. It's a great plan. I really understand. So thanks, Professor. Thanks, Arizo.
Thank you.
It
Thank
was
you
great
very
to
much.
have this
Thank you
work
for
from
your time.
Turkey. Thank you. Let's move to the second paper of the session. It's my pleasure to present the paper Parallax Engine, Head-Controlled Motion Parallax Using Notebook's RGB Camera. It's a full research paper also from Jarbas Jacom, Williams de Lima Costa, Lucas Silva Figueiredo, Jader Abreu, Luana Porcíncula, Pedro Brandt, Luiz Alves, Walter Correia, and Verônica Tahiri from Federal University of Pernambuco, also Fábio Queda Silva, and from André Santos and Elder de Souza Pinho from CD. So let's move to the second video.
Hi, my name is Jarbas Giacomi and I will present you the research Parallax Engine Head-Controlled Motion Parallax using Notebook's RGB Camera. Despite the recent growth of virtual reality industry, head-mounted displays are not widespread like notebooks, and market forecast predicts that the participation of notebooks in daily life will continue high. So how to increase the depth perception in notebook 3D applications without the need of wearing an HMD? Motion parallax is a depth perception cube because near objects change position faster than distant objects when viewer perspective moves. And fish tank virtual reality is an example of motion parallax simulation by changing the 3D perspective according to the viewer's head position. FTVR technologies need to track the viewer's head position. We began this study by asking ourselves, would it be possible to obtain a usable monoscopic fish FTVR using only notebooks RGB camera? We explored three community available RGB face characteristic detection solutions, DLib, PoseNet, MediaPipe, implemented and evaluated two variations of head-coupled motion parallax, and created a client-server architecture that allows quick upgrades for testing new input and output methods. It's possible to classify reviewed papers in stereoscopic and monoscopic, and also in terms of input methods and output devices. This group of stereo studies, for example, from Kong-Silp and Daly, used infrared cameras as input method and 3D monitor and 3D glasses as output device. authors implemented user experiments based on cognitive studies to compare the influence of stereo and motion parallax on depth perception in FTVR. They concluded that stereo is more relevant than motion parallax, but users felt discomfort with stereo technologies. On the other hand, Fafad studies used market-based head tracking as input and spherical displays as output. They also pointed the importance of stereoscopy for spherical FTVR displays. But we also find head-coupled motion parallax studies using simple monoscopic displays. One uses RGB cameras and other kinetic sensor as input, but both focus on traditional LCD 2D screens device like mobile, desktop, and TVs as output devices. We could add our study to the group of monoscopic studies. Additionally, we adapted concept and daily user experiments tests to evaluate our solutions. As we are using RGB camera, we investigated community available face characteristic detection solutions. The DLib's facial landmarks extractor implements the Skazemi and Sullivan paper from 2014, which is still popular and extremely fast. Despite the popularity of this DLib, convolutional neural networks (CNNs) are becoming the first choice for this problem. PoseNet for 2D human pose estimation is very robust, even if only the upper body is visible, which is the case for person using notebooks. We used Ross-Whitman porting of TensorFlow's PoseNet for Python. Finally, to get a richer face characteristic detection option, we explored the face mesh prediction using CNNs of MediaPipe. As a result of this exploration, the parallax engine brings two output effects. The fish tank effect is a monoscopic FTVR using MediaPipe's face mesh, and the head distance from the screen is calculated using the eyes distance in the mesh. And the parallax to DOF is a simple translation of the virtual camera controlled by head horizontal and vertical position variations. It has PoseNet and DLib as input methods options. A client-server architecture get the best of from two worlds. Unity plus C# is great for real-time 3D simulation, and Python is great for easy exploration of academic face characteristic detection solutions. The developer using Parallax Engine prefab in Unity can choose between inputs and output options. User experiments were designed to get information about how users perform tasks related to acuity of depth, space, and displacement of objects using our solutions. The tasks were adapted from concept and daily studies, and the nullity task evaluates how different options of inputs and outputs impact the user's ability to position a rectangular prism in the exact middle point between two other rectangular prisms. The placing task evaluates the user's ability to position the red sphere in the same plane of two blue spheres. The detection task evaluates the user's ability to detect which of the three spheres is moving. Each user executed the three tasks with three different combinations of inputs and outputs. Testers answered surveys before and after the experiment. Parallax 2DOF plus DLib got an elevated placing error and time completion values, while Parallax 2DOF with PoseNet and Fish Tank with MediaPipe face mesh got acceptable results. Users preferred Parallax 2DOF with PoseNet and found it good for depth perception. These numbers aren't statistically significant because we had only 5 users, but they suggest that users may find Parallax 2DOF plus PoseNet and Fish Tank plus MediaPipe usable solutions. We found that different notebooks position and screen rotation have a relevant impact on the user experience. And the use of face characteristic detection for Fish Tank and Parallax Studio F is promising in the context of notebooks. We were able to confirm, as expected, that the DLib face landmark extractor had robustness well below the solutions using CNN. These are the negative aspects of our solution: laborious portability, lack of effects calibration, geometric inaccuracy, update frequency still lower than 60 Hz, tested with a low number of users. And these are the positive aspects: modular, extensible architecture, focus on context of notebooks, possibility of application games without extra hardware, easy to use for Unity developers. Future works possibilities include check if getting the head distance from screen by the size of the iris increments precision, add configurations that allow the adjustment of angulation and screen position, replacement of TCP IP by open south control, and implement face characteristics detection inside Unity. This research have been financed by Samsung Electronic under the auspices of Brazilian Federal Law of Informatics. Thank you very much.
Thanks, Jarbers, for the nice presentation. It's great to have you here. So please to the audience, you can post your questions on the comments here in YouTube, or you can use Discord to send questions. I already had some here. I also had some questions to ask, but I will just keep mine to myself until I have some opportunity. So what is this new error, Jarbers? That Dan Tatsu asked this.
Uh, which sorry, a nulling task, you mean? Okay, the
Yeah,
error in
probably
the
yes.
nulling task, the nulling task, the error is uh, is when the person that is made in the task, the task objective is to, you have two prisms here and one prism here, and the task is to move this prism to be in the middle of the two prisms. Okay, so the right position is in the middle, but if you error, so we have the number of the error, which should be in centimeters, but it's not that quite accurate, but should be sorry, in meters. So
Yeah.
uh, 0.07 is 7 centimeters, but is
Yeah.
not so accurate because we we inference from the eye distance in the mesh. So
Okay, I think it was clear. We have another question here for João Marcelo. Do you believe the parallax experience is harder with smaller displays, such as mobile phones?
yeah, good question. I can only speculate, okay, because I never
Yeah.
in my life tried with mobile, but that's something that motivated us in this research was exactly the fact that the display in the notebook are always, well, at least should be always fixed, okay? So you in front of notebook, you are not moving the display. But with the mobile, you are moving the display. So we have two possibilities. One, use our tool just like it is now in the desk in notebook. Maybe it would be a strange experience because only if you stand fixed with the hand, okay, the mobile in front of you, and you move your head, but that's not a common way to use a mobile, okay? So I think the best alternative in this case should be ally this with slam or to recognize the ambient, and also gyroscope. I don't know the state of art to know exactly the position that the person is with the mobile. And if you add this feature to get the right position of the display in the real world, okay, real world, you could do the same with its digital twin, as it is this screen in the other world, because it's a kind of portal, only visibility portal. You cannot go inside, okay, but you can see what is inside the
Yeah.
fictitious world, the simulated world. So if you can move this digital twin of this portal, I think it would be a very great application, because you could do that, and he should correct the localization of slam. It could add this also rectification for the perception of depth and immersion in this case.
That's great. It's a nice answer because you're changing from the metaphor. So once you are in the notebook, you are the controller of the portal. But if you have the mobile device, you have access to this portal with your hand. So it's a combination of movement. So I understand what you mentioned, and it makes sense a lot. Thank you for the answer. Also, we have another question here from Luis Guilherme. A comment before, great work. Is there a connection between MediaPipe and Unity? do you use Python inside Unity? It's a technical question. Thanks, Luis.
Yeah, thank you for the question. This was well, at the time we test, it was very hard. I mean, to be honest, I didn't try too much time, invested too much time on trying to make Unity face mesh codes, because I tried only one time and didn't work, and then I said, we move up to Python, because Python we could test very fast different CNN alternatives. Not only CNN, but Delib, for example, is old school machine learning. Okay, 2014, not that old. Okay, but uh, but so we could test Delib, we could test CNN from Postnet, CNN with MediaPipe. So that's the reason we used. And Python inside Unity, we also didn't try. I don't remember if we are ready time, but we are now in this moment try different possibilities to migrate to Unity. That's a great question. It's people are working on that all around the world now.
Nice, Jarbas. Thanks. I'm just going to get the token to myself because I'm really curious about this. I had some couple of questions, but I think I'm just going to make one because I saw in your paper, in your presentation, you mentioned the difference in the laptop position. It makes a lot of difference on the result. So if you put the laptop on over the table, or if you put it a little bit upper, it had an impact on the results. So I was curious if you can talk about that more, because it can come from a tracking problem. So maybe the tracker can work not as good depending on the notebook position because of the relative position of the head. But also it can come from the perception of the user, because we have a lot of limitations on the neck movement we can make and the position of our body. So do you have insights about what's the most important to this effect? So the most important problem for that?
Yes, yeah. Thank you very much for this question, Francisco. It sounds like I asked you to ask that, but but no, I didn't. I didn't ask him. Okay, people. But this thing was discovered by chance. Look, because I have a way to use notebooks, which is like I am now, with the notebook a little bit high, okay, higher, in a higher position, different from you, Francisco, that is with the notebook over your table. So the perspective of Francisco views now is like his word is like that for me now, like inclinated. I don't know how to say in English, but it's not like this horizontal, it's inclinated. But my one is horizontal now because of the position of the notebook. So again, if we think this as a portal of our real world to the simulated world, we could view that a simulated world that is like this, with the screen like this, rotated, the notebook rotated, it will do the same effect with the simulated world. It will put the simulated world like inclinated down. So to avoid that problem of difference of way to use notebook and keep it natural, not the user having to think about that too much, we could give the option to rotate this digital twin of the screen in the virtual world to be in the same position of the real screen. Okay, so it was very interesting because I think it was one of the most interesting things. It's a lesson learned, but I think was one of the most one of the best things we discovered. That was discovered because Arlindo, which is the second author and is here in the room, I saw in YouTube, he realized that because he was with the notebook like you, Chico, is now, and I was with mine, and the system was configured to my one. Okay, so a little, this is not working good. This is strange. This, and when he saw my screen, said, "Hey man, we want me to you have to pull in the same way as everybody, because if you do like that, you break the thing, you know." And
Yeah, that's great.
yeah.
It was a nice finding for the community also, because it took my attention on this problem, because you don't expect that to happen. Indeed, you didn't mention about tracking errors, so probably tracking is not a problem. The problem is about the perspective of the user. So that's a great thing to find. So it's a nice finding from your paper. So thanks and congrats for that. I believe we can end by here, Jarbas. Thank you again. Also to remember to everyone, you can also discuss with Jarbas and with Dr. Baharu and Arizo after the session. You can send questions to Discord or this YouTube. But we are going to move now for the third paper of this session. Thank you again, Jarbas.
Many
and it's
thanks.
another paper, yeah. And it's another paper from Turkey. It's my pleasure to present the paper Enhancing VR Experience with RBF Interpolation Based Dynamic Tuning of Stereoscopic Rendering. It's a journal paper from Computer and Graphics Special Session for the SVR. It's a paper from Ufuk Selikan, Emre Avan, it's the author and presenter of this paper with me here, Tolga Kapin, and Hazmet Gurkay, all from Hacettepe University in Turkey. So let's see the third video of this session.
Providing a depth-rich virtual reality experience to users without causing discomfort is still a challenge with today's commercially available head-mounted displays, since they constrain stereoscopic rendering parameters to keep visual discomfort to a minimum. However, these measures often lead to an unimpressive VR experience with a shallow depth filling. We define a novel method for dynamic tuning of stereoscopic rendering parameters where radial basis function interpolation and projection matrix manipulations are used to create a better VR experience. Our proposed method is primarily intended for guided VR experiences such as VR walkthroughs or VR rides, assuming a depth layout defined by a path of depth-altered waypoints which contain stereoscopic camera parameters in the virtual environment. Results of the user study indicate that our approach with proper depth altering enhances user experience in terms of overall perceived depth and picture quality, while maintaining visual comfort just like the HMD's default arrangement. Our approach consists of two parts, VR authoring and VR experience. In VR authoring, the user creates a depth layout for a VR experience to create a depth narrative for the scene. The depth layout is composed of a series of waypoints. By placing a waypoint, the user defines a pair of position and view orientation and sets the stereoscopic camera rendering parameters for that position. During authoring, the user is immersed in the virtual environment. Therefore, the user can tailor a depth narrative to that virtual environment from the first-person perspective using the same type of display that viewers will experience the scene with. These parameters and angles are defined according to the depth perception of the user, which makes our approach a suitable solution for enhancing user experience in VR. VR experience is the main component of our approach, where our proposed solution continuously updates the two major stereoscopic camera parameters, which are interaxial separation of the stereo camera pair and their convergence distance while following the camera path. To update stereo camera parameters, we use radial basis functions for the interpolation of the stereoscopic rendering parameters scattered through the 3D scene. Due to its dependence on second-order differentials, it ensures high smoothness of interpolated parameters. In VR experience, while the cameras follow the defined path, the projection matrices of the two cameras are updated according to the parameters, interaxial separation and zero parallax distance, based on the output of the RBF. In planar stereoscopic displays, both cameras have asymmetric projection matrices that together create a single viewing plane at the selected zero parallax distance. Since there is only one display for the eyes to converge and focus on, this method is suitable for those displays. However, for the HMDs, there is a dedicated display for each eye, so using this method just as it is isn't possible. The figure shows the view frustra of the cameras from a top-down point of view. When alpha is larger than beta, it triggers eyes to rotate inwards. As the difference between alpha and beta gets larger, the viewer's eyes rotate and more inwards, which creates the feeling of looking at a nearby object. To create a single image in our proposed method, projection matrices for the left and the right eyes are swapped, so the cameras are directed more outwards as the zero parallax plane comes closer, and less outwards as the zero parallax distance is set to a farther distance to direct viewer attention properly. Unless additional measures are taken into consideration, a dire drawback of this method is its sensitivity to zero parallax distance. Diplopia will occur at large zero parallax distances, and small zero parallax distances will cause eye strain and fatigue. To solve these issues, our system restricts zero parallax distance in a dynamic range according to the immediate interaction separation distance that lets the difference between alpha and beta change from -10 to +1 of the HMD's default. We conduct our evaluation using two different scenes. One of these takes place indoors in a school gym with multiple animated athletes and sports fans. The other one is an outdoor scene with multiple animated human characters on a suburban residential street. Maximum rendered depth is considerably higher at the outdoor scene. The subject's focus may change more abruptly or frequently between far and near regions when more depth is available, and this may cause visual fatigue and eye strain if the evaluated setting does not offer proper compensation. We test users' self-created paths and predefined paths in both scenes. Results of the user study demonstrate that our method, with proper depth authoring, significantly enhances user experience in terms of overall perceived depth and image quality. Moreover, predefined paths increase the user experience in both scenes. Our proposed method slightly improves the visual comfort on average as well. However, the improvement isn't statistically significant. In this paper, we have introduced a new method for depth tuning of stereoscopic rendering for real-time automated stereoscopic camera control in virtual environments that are rich in depth. Our method makes use of RBF interpolation and novel projection matrix manipulations for the aim of delivering enhanced depth filling by dynamic yet smooth depth adjustments. For more information, please check our paper.
Thanks, Emily, from this nice talk. It was a great paper. Nice to see your work. It's quite interesting. I have some questions here, but also I'm going to say to everyone, if you have some questions to Emery, you can send it on the comments here in the YouTube or in the Discord. But I'm going to get the token to myself, so I'm going to use this fast while we don't have questions. So, Henry, congratulations for this work. It's a great thought. These are the type of studies, also with the work from Jarbas and from Arezzo, that you think deeply on the parameters and how we feel them. We also had some studies here to understand how movement impact on reading, for example, inside a car or inside a vehicle. And it's quite interesting to try to understand that. So you try to work with that in a very clever way. So congrats for that. And you mentioned about the visual comfort that you had some improvement. So users related that, but it was not statistically relevant. So I don't know if you have thoughts about why the visual comfort was not that impacted, and why is this difference, or even more, how do you intend to act to improve this visual comfort, the analysis or the ideas that you have to work with this question?
I really like that question. Thank you so much. First of all, our method is mainly for the VR rights or VR walkthroughs. So users do not use their head movements while they are seeing the scene. So while we are testing, we said the two testers, do not move your head and stay still. So it is not easy thing to do. So there's a little jitter, little movements, and especially our testing. I don't remember, but maybe 15 or 20 minutes. It consists of 20 minutes. So as the time goes by, the users will become tired and the head movements become a bigger. So while you are moving your head and do not see in front of your eyes, it's a little bit of issue. So it may become a huge problem for some of the peoples. Even one person in the testing said that it become a nauseated. Other than that, other users do not say that. So maybe the reason the comfort is statistically lower than the other results is this. In order to solve this, I think we need to change the algorithms of our algorithm. Like, and we also want to do that, but because of the COVID-19, we didn't find any other tester. So, in our honest opinion, I think we need to change our algorithm just like that. I'm sorry. Let me think about that first. We, in this work, change the camera parameters. So users define the parallax and zero parallax distance and the camera IPD, inter camera distance. If we give importance points to the objects in the scene and develop the camera parameters according to these importance points with using RBF, I think the scene will become more interactive and user can rotate and jitter without any discomfort, and it will solve this issue. But again, I said that because of the COVID-19, we couldn't do that.
Yeah, but indeed, it's a great idea. So you basically are moving from a static at some point approach to a really or true adaptive approach. So that this could be a nice step to your work. So try to going further on this discussion. How about this adaptive behavior of your system by using some gaze tracking? I don't know, probably you think about this as a future work, as I saw on the paper, but I don't know if you already experiment something, if the precision of the gaze tracking systems are enough for you to make this fine tuning of the system, for example, live. So maybe you don't need this preset or this analysis from the user on the authoring tool, and then you can just do it live. So what are your comments on this?
This is the second future work in our opinion, but there is a little bit of issue with that. If we alter the projection matrix, the stereo projection matrix, the user's eye will rotate inwards or outwards. So the actual position, the user's eyes will change accordingly. And I don't remember the actual function, but maybe it's the get projection row and set stereo projection row in Unity. It didn't. This thing doesn't call with trackers. We already use this tracker, but it in very small distance or on a large distance, there'll be a little of parallax issue. So we didn't find the exact position of the users. So we had to get back from this and use the papers method. But thank you for that. We always wanted to use that.
Yeah, it's because it's something that directly comes to our minds. Okay, you have a great system, you have some nice ability to understand how to improve the experience from the user, but we are always trying to be as more interactive as we can. So to be more adaptive. So I really understand and I agree with you. The next steps of your work would be to go to this adaptive path. It's quite nice. So we still have some minutes. I don't know if someone has any last questions for your work or maybe for some discussion. I understand that your work and the work from Jarbas and from Arizo, they have lots in common. I was also curious about, for example, the analysis on the parameters that Jarbas make, for example, or the understanding on the field of view that Arezzo is working with, how they can impact your work. So probably you can discuss later with them also to try to find these intersections from your papers. And I believe it's that for today. I don't know if there are some final questions. I can wait for some seconds on that. I don't know if I have some final comment, Emery, or on your work or your paper.
I don't know. It's really quite hard thing to do. It's my first paper.
Yeah, you did it
And
great.
thank you so much. I hope that with the future work, we can show we can display our work, and with it can be used with other people, other systems. I hope that. I really do hope that.
Yeah, that's great. So you have the right inspiration to do science. So to have others using your work. So congratulations for that. So thanks, Emery. I'm just going to move forward to finish this session. I believe it was a nice session with great discussion. Thank you all for the discussion. Thank the attendees for the questions and for being here with us. It was a great pleasure. So I'm Francisco Simões, professor here in Recife, Pernambuco, from Federal Rural University of Pernambuco, and also a researcher from Voxel Labs. And I will close this session now. Thanks for the organizers, and let's keep moving with this great SVR 2021. Bye-bye. Thanks.
Thank you. Bye-bye.